Hello, welcome to the course Electronic System Design. Last lecture we discussed some topics about RF PCB design. RF PCB is something which is designed for high frequency applications and particularly for radio frequencies. The frequency range is significantly higher than our standard PCBs. We have up to the gigahertz range in the RF PCB design. Today we are going to see what are the factors which affect these RF PCB design. For example, designing a trace, a simple connection from the input to output, significantly change the performance of the whole PCB if it is not designed properly. If this is designed properly, the RF PCB will work as desired. However, slight change in the thickness of this PCB, of this microstrip or the length significantly impacts the performance of complete RF system. So, today we are going to see some of the factors which directly impact the performance of RF PCBs. So, designing a PCB for radio frequency applications is very different from designing a board for typical digital logic applications. So, even small changes in layout geometry or component selection can make the difference between a board that achieves the desired performance versus the one that underperforms or is prone to stability or oscillations, which are reliability issues. Even small changes in layout geometry or component selection can make the difference between a board that achieves the desired performance versus the one that underperforms or is prone to instability or oscillations. And the next point is managing the parameters like transmission line properties and impedance matching accurately across the RF signal chain on a PCB impacts the overall system design performance. And impedance matching accurately across the whole RF signal chain impacts overall system performance. So we have these RF PCBs which are vastly different than our high speed digital PCBs in a design way. Even a small change in the layout geometry or the component we select, that significantly impacts the PCB performance. One PCB which is designed very accurately, very carefully, it can achieve the desired functions. However, if one PCB, which is RF PCB, is not designed very carefully and there is a mismatch or impedance matching mismatch is there, a small change in the layout geometry or component selection can create this PCB to underperform, or there can be some reliability issues such as the oscillations and ringing. If there is a mismatch, the signal will be bounced back. Because of that, there will be instability in the system. So, RF PCB need to be designed very carefully considering all these factors. One factor is, for example, is the managing the transmission line properties across the RF signal path. So, signal is generated from a source, then it goes to first component, then goes to second component and so on. Across all this signal chain, we need to perform the impedance matching so that there is no signal reflection at any interface. So, we need to make sure all the interfaces are terminated to a standard termination, which is 50 ohm termination we consider for RF systems. So, everywhere the line or the component input and output should be terminated properly at 50 ohm termination, and the transmission line, which is nothing but the tracks on the PCB, we need to carefully maintain the characteristic impedance of these traces throughout the signal path from the starting of RF signal to the termination or the far end of the system. So, we need to make sure everywhere this is terminated to a standard 50 ohm termination. So, these are some of the factors, and now we see what are the critical factors. For example, the operating frequency, how does it impact the PCB design of a for a radio frequency applications. So, let us see how the operating frequency impacts our design. So, operating frequency is the first parameter which is decided before starting the RF PCB design, and RF PCB layout through which we are going to design this RF PCB, this approach varies tremendously across the frequency spectrum. For example, at the lower PCB we have lower frequencies PCB, we have different approach of RF PCB design, but for the high frequency RF PCBs we have entirely different approach for PCB design. The RF PCB layout approach varies tremendously across the frequency spectrum. So, for lower HF or VHF bands, surface traces will suffice. So HF is the high frequency and VHF is the very high frequency band. So these are the bands. In these bands or lower these bands, even a simple surface trace will be enough for propagating the signal, which looks something like this. We have a standard PCB here. This is FR4 substrate. The back side is the copper plane, and on top we just lay down one trace. The width and length is not very significant to design for these HF and VHF bands. Any standard width of trace will be suffice to propagate the signal. However, for UHF band or ultra high frequency bands, UHF and above frequencies, microstrips or strip line are used in dielectric substrates. Which looks something like this. We have the substrate here and the bottom is ground plane, and on the top we have this microstrip. And the width of this microstrip is carefully chosen or calculated so that the characteristic impedance is always 50 ohm standard. So we design it in a way that characteristic impedance is always 50 ohm and the termination at the far end is also 50 ohm standard termination. However, if the frequencies are very high, then we sometimes use the waveguides. The waveguides look something like this. We have the hollow space in between and these boundaries are metallic, and this is like a tube type of structure. This is the length. One side we apply these microwaves and on the other side we receive them and they travel inside these waveguides. So for very high frequencies we use this. However, for normal RF PCB design we mostly use microstrip or sometime strip lines. So majority of RF PCB we develop these microstrips. Now let us go to the second factor which impact our RF PCB design, which is dielectric constant. So the dielectric layer which we put between these metallic layers, that heavily influences the impedance and velocity of RF traces. So the signal is travelling in the metallic traces, but what the dielectric material we use below these traces, that also impacts heavily the impedance of these lines as well as the velocity of our RF signal within these traces. The dielectric layer heavily influences the impedance and velocity of RF signal in traces. These materials and their stable dielectric constant allow controlled impedance traces to be created. So these materials and material with stable dielectric constant allow controlled impedance traces to be created. So if we have a material where the dielectric constant is very stable, it does not change with temperature or does not change with the frequencies, that allow us to make traces with very controlled impedances. And common substrate for use for RF use are FR4, which is standard substrate for PCB design. There the dielectric constant is around 4.5. Then we have another substrate which is Rogers. There the dielectric constant is typically 3, though it changes with the product you want to choose. In Rogers they have many PCBs. And ceramic filled PTFE. Composite. So see, these are some of the substrates we use for RF PCB design. For lower frequencies, in RF, we can still go for FR4 substrate where the dielectric constant is 4.5. However, for the high frequency range, we need to go to other substrate like Rogers or ceramic filled PTFEs. In these materials, first thing to note is the dielectric constant, and the other important parameter to look out for is the loss tangent. So, while selecting these substrates, we check for the loss tangent of those materials. So, all these dielectric material, when we apply high frequencies, there are inherent losses which are quantified by the loss tangent, or we call it by DF. To understand that, let us see the cross section of a trace. So, this is the cross section. On top we have this microstrip and we are applying the signal here. At the bottom we have ground plane, and these fields are originating at the microstrip, both the side, top as well as bottom, and are terminated at the bottom plate, which is our ground plane. This is metallic, maybe the copper or some other material. This is, let us say, copper on top, which is patterned in a microstrip line. Now, these electric lines, electric field lines, are originating on the top and going all the way to the bottom. Now, the frequency of this signal is very high. It means in 1 second the signal is going up and down many times if we consider 1 gigahertz frequency. So, in 1 second 10 to power 9 times the signal is increasing and decreasing, assuming it is a sine wave. So, the frequency is 1 gigahertz. So, all these fields which are generated by these microstrip, they are also switching at the frequency of 1 gigahertz. So, when the signal goes high, for example, these field lines will be originating from the microstrip and terminate at the bottom. Then the signal goes down, becomes 0, then these field line disappears. Then again when it goes negative, then these field line again appear, and again when the signal goes 0, they will again disappear. So, at 1 gigahertz of frequency, these field lines are also getting generated and disappearing. So, at that high frequency, if these field lines are going through this substrate, which is our substrate here, and there is a potential as well, because this signal is, let us say, 10 volt peak to peak. So, because of that voltage, these field line has certain strength. So, these fields can produce some extra charge in these substrates, and because this is induced charge, this charge is also appearing and disappearing based on the signal applied. So, this creation of this induced charge and disappearing, this actually consumes energy from our electric field. So, this is the electric field which we are generating by the signal, and if this charge has to appear and disappear at 1 gigahertz frequency, this energy which is needed to appearing and disappearance of this charge will have to come from the signal itself. There is no source of extra energy in this whole system. So, this extra power which is being used here, that should come from the signal itself. So, our signal strength will go down. It means our signal will have certain loss in propagation due to the frequency of that signal and of course the voltage. So, our signal is degrading or having loss while traveling from point A to point B, and that is because some of the loss is being happening inside the substrate itself because of this charge induction. So, this is how the charge is being induced in the substrate and the extra loss appears in the substrate. This loss is generally measured using this parameter, which is loss tangent. So, dielectric materials have inherent losses which are indicated by the loss tangent. Indicated by the loss tangent. dF. For this reason, we need to choose a material with a low loss tangent so that the insertion loss of the transmission line is minimum. So, we need to choose a material low dF to minimize insertion loss in transmission lines. So, transmission line can be anything, it can be microstrip or strip line or CPW. We need to choose a material with low loss tangent. It means the loss should be lesser in the dielectric so that the insertion loss is minimum. Insertion loss is a loss when we insert something in the signal path and calculate how much is the loss generated due to this extra component which we are inserting. So, that is how the insertion loss is calculated. For this, we have glass microfiber substrates. There are special substrates, glass microfiber substrates offer exceptional EF and well suited for wireless applications. So, these are some of the points while choosing the material itself. The first step for RF PCB design is to figure out the frequency, what is the maximum frequency RF PCB has, and then as per this frequency we need to find out which material we need to use. So, for every material there is a loss versus frequency graph available with the manufacturer. You can go through that graph and figure out how much the loss will be there for that particular frequency range. So, we look out for the dielectric constant first. What is the suitable dielectric constant? We want to go for FR4 or Rogers. And the second is the loss tangent. Because our frequency is high, we do not want the signal to have higher losses in the PCB itself. So, we choose the material carefully so that the loss tangent at that particular frequency is lesser and our signal can propagate without any degradation. So, this is how we choose the material. The next step is to choose the components. As we have discussed, when we make schematic, we use only symbols to design the complete schematic. However, we know that this is a RF PCB and we need to very carefully put these together so that the signal does not degrade. We need to choose these footprints very carefully so that they have lesser parasitics compared to the other version. For example, we are using 100 ohm resistance in our schematic. Now we have multiple options of putting this 100 ohm on the PCB. We can go for a big resistance where this is a through hole component, 2 lead wires will come out and we will dig up 2 holes in the PCB. We put these lead wires into that and solder it. This is one way. The other way is we use SMD component, which is very small component and need not to drill a hole in the PCB. We make the pads on PCB, put the SMD component on top, heat it up so that the electrical connection is made. This is one way of doing it. In this case, the parasitics will be less. So, by selecting the components properly, we can improve the performance of RF PCBs. So, first choosing the component, first we need to make sure the impedance matching in the RF PCB. So, as RF signal encounter discontinuities from traces to pads, vias and components, abrupt impedance mismatch causes problematics signal reflections. So any discontinuity or any interface if we have in the signal path that act like a boundary where the signal can reflect. Next point is the component selection. So all components have parasitics. So no matter what component we use, all components have certain amount of parasitics, but they are specially pronounced at higher frequencies. So for example, we have 100 ohm resistance to put in the PCB, and now our frequency of operation is very high, and we have multiple options of putting this 100 ohm on PCB. One is, let's say, this case on the extreme right. This is a resistance where is a through hole component. Through hole component is something like this. We have this resistance, and these are two lead connecting wires which come out of it. We drill the hole in the PCB or this substrate. So this is your substrate. In this we drill the hole and bend these wires into this, solder it on the back side here. This is how we connect this 100 ohm resistance. So this is our 100 ohm resistance. Now the problem in this case is, at lower frequency this will work fine, but at higher frequencies we have so much of parasitic capacitance as well as inductance. So whenever we have a wire, these are extra wires coming out of these resistance. Resistance is only this much. This is the overall resistance. These are just connecting wires. If these connecting wires are long, they offer parasitic capacitance, resistance as well as the inductance in the path. So when the signal travels through these wires, that experience these parasitics, and the signal will degrade. Moreover, this extra length can also act like a antenna or stub at higher frequency. So this is a poor design for RF. Same thing, we can improve it by using SMD component, where SMD component is like this. We do not have these extended pins coming out, only on the corner, both the corners we have these connecting metallic layers. So on both the sides a metallic surface is there. These are there to make the connection. So now instead of these long wires, we have just a small metallic surface which need to be fixed on PCB. Here it is shown one example. This is our 100 ohm. resistance, and this is the solder which we use to solder it on the PCB. So, this is much improved in the frequency response compared to this right one. However, still if the frequency is very high, then even this much amount of solder can create extra parasitics, the capacitance, the fringe capacitance from this solder to the neighboring ground plane. This is also sometime unacceptable. So, we can go even to the further improvement in this. We choose a resistor which is very small in size and thickness. So, here the thickness of this SMD component was bigger. We can go for a very small geometry resistance. This is also 100 ohm resistance, and now only this much of solder is used for making the connection. So, the effective parasitics are less. If parasitics are less, we can operate it at a high frequencies. So, this is a better design compared to the right one. However, the power handling capacity of these components here, if the component is smaller, the power handling capacity is generally lesser. So, there is a trade off. We can go for the higher speed, but not at the very high power in these RF systems. So, there is always a speed versus power trade off. So, these are some of the points which we discussed today to watch out for when we design a RF PCB. RF PCB design is entirely different than a standard digital PCB design, and we need to be very careful in material selection first. What material we need to choose, that depends on what frequency we have in the RF system. Then the component also we need to select very carefully so that the losses occurred due to these components are minimized, and the losses occur generally by these parasitic capacitance, inductance and the resistance they have. If we have a longer wires coming out somewhere, that is going to create the extra resistance and inductance in the path of signal, and that may degrade the signal. So, these are some of the points we need to check very carefully. Now, let us see a real PCB which is designed for the RF applications and see what are the techniques used or what are the factors which impact the performance of RF PCB. So, for that we go for a publication which is openly available, some images at least, through the IEEE website, and we will see how the RF PCB is actually prepared and designed. So, for this we just go to IEEE website. For this we need not to have the login or paid subscription to RF for IEEE papers. We just check this title on IEEE website. And all these images are already available. So, we go to IEEE website, which is IEEE Explore website, and check out this title which we are taking here as a example today. So, when we go to this page, we go down on this page, these images are available. So, this is the schematic of a standard RF system, which is nothing but a RF power amplifier. So, in this schematic, if we see, we have in the center the silicon chip where our power transistor is there, and we have other components. For example, this is the RF choke coils we use for RF in the RF power amplifiers. These are supply connections, the drain supply voltage and the gate supply voltage. These are the RF traces where the RF signal will travel from the input to the output here. And these RF choke coils are there to boost up the signal. On top we have this capacitive ladder. This is there to minimize the ripple in the supply voltage, because when the power amplifier will turn on, this will draw huge amount of current. So this supply, which is let's say standard at 5 volt, this can also shake because of this high current surge. So to maintain it at a standard level without these ripples, we use these decoupling capacitors at the supply. Similarly, we use it at the gate as well. At the gate we also use stability network, which is resistance and capacitance. And these lines from the drain and from the gate, input to the gate, these are RF traces, need to be designed carefully. This schematic was designed for 1 gigahertz frequency. Let's see how the PCB look like for this particular circuit. So this is the RF PCB. On the bottom we have this RF PCB photo. How it look like. In the center we have this silicon chip, which is acting as a power transistor, and how it is put on this PCB, it is shown in the above figure. We have this low loss laminate in the center. On bottom we have this copper ground plane, which is G and D. On top we are making these traces. These are copper traces. They are like microstrips. And in the middle we have this copper ground plane, or over which the chip is pasted using thermal conductive epoxy, because we need to maintain the temperature as well within the limit. So we use thermal conductive so that the heat generated within the chip will be dissipated. And the connection we make using these gold bond wires from the pad to the traces. So this is how the chip is actually put. Now this is the complete photo we have for RF PCB. These are input and output terminals of this power amplifier, and we are feeding supply at these islands. For example, this is one, which is VGG or gate voltage. This is the RF in, this is RF out, and this is our drain voltage. These are choke, RF choke, and these are our microstrips. These are our microstrips. These are carefully designed so that the characteristic impedance of this trace is 50 ohm at 1 gigahertz. This is input trace and this is output trace, and the rest of the portion of PCB is put at ground through these multiple holes. So this is how this PCB actually look like. We can write down some key considerations. So here we use gold bond wires. Are used for connection each bond wire has around 1 nanohenry inductance for 1 centimeter, typically 1 centimeter long length, and this inductance is actually parasitics, which should not be there, but we use this wire. If the wire length is typically 1 centimeter, then we get around 1 nanohenry of parasitic inductance, which is undesirable and significantly degrade the performance of RF PCB. Here we use thermal conductive epoxy for thermal management. The substrate here we use is not FR4, this is Rogers Duroid substrate. For low RF loss. We use multiple deep coupling capacitors here. To filter the noise from the supply rails. We use stability RC network. To stabilize the power amplifier. So these are the components we use for stability in our circuit, and we use all SMD components to reduce parasitics. So we saw today that some points need to be taken care of while designing RF PCBs, and we saw a RF PCB schematic where we are developing a RF power amplifier, which is a large signal circuit and operate at very high frequencies such as 1 gigahertz or above, and this is the PCB which is designed for that particular schematic power amplifier. And we saw that there are certain factors we need to take care in the RF PCB design which are generally not there in the high speed PCB design, such as the bond wire inductance. When we connect the components even with the gold bond wire, that also offers certain amount of parasitic inductances, and inductances are very bad for the RF signal propagation. So, because RF signal is switching at very high frequency, inductance opposes the change in its the current. So, the signal is generally blocked by these parasitic inductances. We use thermal conductive epoxy for managing the thermal the temperature generated by the chip, and we use special substrates for having low loss tangents, and we use stability network because all these at these high frequencies circuits generally become unstable. So, we need to stabilize that using some special RC network, and we use most of the time the SMD components, so that the parasitic effects of these components are lesser and we can achieve a higher frequency at RF PCB design. So, that is all for today. Thank you.